angle in the upper segment using this chord, like this. If we draw a second angle like this one, or even a third like this one, then all of these angles must be the same size because they come from this chord and they're in the same segment. So if the purple one was 68 degrees, the green one would be as well, and so would the blue one. Sometimes this theorem is drawn without the red chord, so we can remove that and it may look something like this, and the property still holds. It's often drawn with only just two of the angles, so if we remove one of them like this, we end up with this picture where both of the purple angles here are the same size. You can also apply this theorem by drawing a chord here. If you do the same thing as we just did but upside down, you can show that these two angles are also the same. And again, we don't need to draw that chord, so very often you'll see this theorem drawn like this. It's sometimes informally referred to as the bow tie theorem because this looks a little bit like the shape of a bow tie. In an exam though, you want to avoid that terminology and say that the angles in the same segment are equal. But if the bow tie helps you recognize when this is true, then that's fine also. For the next theorem, we're going to need to mark on the center of the circle. We're going to draw a chord that goes straight through the center. This is known as a diameter. If we now do the same thing as we did for the first theorem, so draw angles that are in the same segment, we know they're going to be equal. So if we draw one angle like this, a second like this, and even a third like this, we know all three of these angles must be the same size. But it turns out that if the chord that you draw happens to be the diameter of the circle going through the center, all of these angles will always be right angles. So the second theorem is that the angle in a semicircle is 90 degrees. We say this is the angles in a semicircle because that diameter splits the circle in half. For the next theorem, we're going to draw a chord once again, and draw an angle at the circumference also, but rather than drawing another angle at the circumference, we're now going to draw an angle at the center, but using the same chord, so something that looks like this. If the green angle at the circumference of the circle was 50 degrees, then the blue one would be twice this, 100 degrees. So for this theorem, we say the angle at the center is twice the angle at the circumference. You could also say it in reverse, the angle at the circumference is half of the angle at the center. Once again, this theorem still applies if we remove the chord, so sometimes you see it drawn like this. For the next theorem, we need to learn some more terminology. If you draw a quadrilateral where all four of the sides touch the circumference of the circle, this is known as a cyclic quadrilateral. Now it's only true if all four of the corners of the shape are on the circumference. For example, this shape here is not a cyclic quadrilateral because this corner here isn't on the circumference of the circle. So let's return to our original one. This is a cyclic quadrilateral. The theorem states that the opposite angles in a cyclic quadrilateral had to make 180 degrees. For example, if we look at these two angles here, they're opposite each other and they're in a cyclic quadrilateral. So if we knew that this one was 86 degrees, we'd know the other one must be 94 degrees, since 86 plus 94 makes 180. Similarly, these two angles must add up to 180 as well. If we knew this one at the top was 110, the bottom one must be 70, since 110 plus 70 is 180. For the next theorem, we're going to draw a tangent to the circle. A tangent is a straight line that touches the circle in one place. We're then going to draw a radius from the center of the circle to the point where the tangent also touches the circle. In this diagram, this angle here will always be a right angle. So we can say for this theorem, a tangent meets a radius at 90 degrees. Now if we stick with this same diagram, we can do some more theorems. If we create a point at the end of this tangent on the right hand side and call that P, and then if we draw a second tangent from P to the circle, it would look something like this. If you measured this distance here, from P to the point where the tangent touches the circle at the top, and the same distance at the bottom, these two lines would be the same length. We don't normally show this with arrows though, we usually draw a line across both of those lines to show they're the same length, like this. If you were going to write this theorem down, you could say that tangents from the same point are equal in length. We can also add a bit more information to this diagram. If you draw the angle at P, then draw a line from the center of the circle to P, then this line will split that angle in half, or we could say it bisects the angle. So if the whole angle here was 30 degrees, then we'd have 15 degrees on the top and also 15 degrees on the bottom. Now we're going to move on to the final theorem. If we draw a tangent
between the tangent and the chord through the point of contact of the tangent is equal to the angle formed by the chord and the alternate segment. Now this one's a bit complicated, but I think if you look at the diagram, you'll understand how it works.